Welcome to a course on measure theory and integration. In this course, we'll initially start with the concept of Lebesgue measure. But before getting into the concept of measure theory, we would like to recall few things from the basic set theory. First of all, let me tell you what was the approach that was done by the man called Lebesgue. What was his work initially? Okay, in we all might have come across the course on real analysis both in our undergraduation as well as in post graduation. Okay, this is the fundamental thing that is needed to study measure theory, right? Okay, in real analysis, okay, some might have studied the concept of Riemann integration in our undergraduates itself, and some might have studied in post graduation. So in post graduation, all might have come across Riemann Stieltjes integration as well. Okay, now let me just stick to Riemann integration, right? In order to perform a Riemann integration, we need a bounded function, okay, which is defined on an interval. So by bounded function, what I mean is that I need some bounded interval. Okay, or instead of saying it as a bounded function, I may say it as a continuous function precisely, or it may have some point of discontinuity which should be of the first kind, right? That means a jump discontinuity is allowed. So we must have some bounded interval. In this case, what we do is that the area under a curve between these two lines, that is in this interval, is the integral value. So this was the approach. But what was what was the Riemann's theory? In Riemann's theory, we split this interval AB into subintervals, and we look for the maximum and minimum possibilities. If we are looking for the minimum possibilities, this is what we would get. Okay, we approximate we approximate this total area by the area of these rectangles. Okay, we add up these rectangles and finally that area is going to be the resultant. So this is the lower Riemann sum ideology, whereas the upper Riemann sum is we look for the this case. Okay, so we calculate this area of these rectangles we calculate, and finally we add them up, and the resultant is assumed to be the integral value, right? So these rectangles has to be taken over very small, that is like we'll have to divide the entire interval into as many possible subintervals, and the length of those subintervals should be very very small, that is the length may approach to 0, right? So we'll have to consider such intervals, and with those ideologies we have done these things, right? This is Riemann ideology. Okay, there we had the function f which is defined from AB to R basically. Okay, so here this is happening, we subdivide the domain and look for these things, whereas Lebesgue's approach is that we find the range of the function. Okay, we will subdivide the range and we look for the inverse images of these things. If we take these things to be I1 I2 etc, goes like this till some in, we look for the inverse images of these things, and with the help of these inverse images only we will calculate the integration value. That is the ideology of Lebesgue. Okay, So let me tell again what I said. Let me The idea of Riemann is to decompose the domain and find the integral value, whereas in Lebesgue's approach we decompose the codomain and take the inverse images and attach lengths to it. Okay. For example, I can give you a small example kind of a thing. Okay, let us consider a step function. Okay, the step function that I'm going to consider is, okay, let this be my x and let this be my y, which is f of x. So for the sake of simplicity, I take the interval 0 to 1. Okay, I subdivide this into 4 intervals. Okay, in these intervals it takes some values like this. Okay, let this point be alpha 1, let this be alpha 2, and this be alpha 3, and let this be alpha 4. Or you may write the way you want. Okay, some example. So here, what is happening? So we have subdivided these into subintervals. Actually, we have divided the interval 0 to 1 into 4 subintervals. Right? Here, your step function means what? This function is not continuous, but it is defined on some bounded interval. It has only jump discontinuities, hence the integration value can be found. Right? If you try to integrate this one over the entire interval I, which is from 0 to 1, so what we do? So this is the length of this interval. I don't know what is the length. So let me write it as L of I1 length, which is to be multiplied with the function value, supremum value or infimum value. I'll have to take here the function value is alpha 1 itself. So alpha 1 times of length of I1 plus alpha 2 times of length of I2 plus alpha 3 times of length of I3 plus alpha 4 times of length of I4. This is the integral value, right? Now, the Lebesgue approach is we look for the codomain. Here, what is the codomain? That is simply alpha 1, alpha 2, alpha 3, and alpha 4. Okay, so let me take only this alpha 1. Here, what is f inverse of alpha 1, which is I1? Okay, f inverse of alpha 2, which is I2. So, in general, let me take f inverse of alpha j is ij here, right? For j running from 1, 2, 3, 4. Now, we will have to attach the length of these things. So that is summation j runs from 1 to 4 alpha j length of these things is the integral value. So this is the Lebesgue's approach. Okay, here with the help of step function, I have given you the example. This might seem quite easier one, but when we get into the lecture of the contents of our lecture, you will come to know what exactly the approach of Lebesgue is. Okay, these are some topics, that is the Lebesgue integration, which we will see in the second module. Initially, now let us start with some basics in set theory. So, set theory means what? We basically start with a set, right? So, whenever we start with a set, we must clearly know the definition of a set. A set is a collection of well-defined objects. Okay, so in the definition, we have the term well-defined. This must be understood very clearly. Okay, since you are a postgraduate student, I leave these things to you people. to recall what you have studied till now, right? So the notion of union, intersection, difference, all those things, I assume that is known to you, right? Now let me get into the definition of algebra of sets. Okay, here we are going to collect the subsets of some set. Okay, here X means it is some non-empty set. Okay, it can be any type of a set. Okay, basically we need a set to define algebra. Okay, the collection of subsets is called an algebra or Boolean algebra if it satisfies the following conditions. What are they? Union of any two sets in this collection must be a member of the set itself. If the set is present inside this collection, then its complement must also present in it. Here, A bar represents the complement of A. If you don't want to write in this notation, you can simply write this as A complement in your usual notation as well, right? It is completely up to you. Okay, and the intersection must also be inside the set itself. Okay, so here they have said that the first condition follows like the third one just follows from the De Morgan's law and the first condition itself, right? So with the help of these algebra sets, here we are going to define something called sigma algebra. That is very important. Okay, that is very important in the course of measure theory and integration. Okay, so we have and basically we have an algebra. So whenever we talk about algebra, it means what? So it means if A and B are in script A, then A union B must be in script A, then A complement must be in script A as well as B complement also. For all the sets, it has to be true, right? A intersection B must also be in script A. Okay, this union shall be extended for any number of sets. Okay, as well as the intersection. So these conditions has to be satisfied. This algebra is called a sigma algebra if every union of countable collection of sets in A is again in A. Okay, what are they trying to say here? So let us try to redefine sigma algebra. Okay, a collection A of subsets of X, which is any set basically, is called algebra if the first condition for A1, A2, it goes, which are members of the script A. For the sets in script A, union I runs from 1 to infinity, AI must be a member of A. Here they said every union of countable collection. Okay, so you may take any number of, okay, any possibility of countable collection from the given collection of subsets, their union must be inside A. Okay, the second condition is A is in A must imply A complement is also in A. Okay, I mean the set's complement. The third one is for A B in A, we must have A intersection B is also a member of A. Okay, more precisely or more generally, we can say if a1 a2 till an is in a, then intersection I runs from 1 to n, ai is in a. Okay, so these things may be simply known as, this is the condition of closed under countable union. Next is closed under complement. This is closed under finite intersection. So one has to be very careful about using this union and intersection in sigma algebra. Okay, here you might have noticed that it is closed under countable union, which means even if you take infinite number of subsets of a particular set, that is not a bother. If the collection that you have taken is countable, then the union is going to be inside that thing. If it is so, then only we can call the collection to be a sigma algebra, right? Whereas when we come to the concept of intersection, it must be a finite intersection, right? So with the help of algebra, we shall have a result, and that is the thing that I am going to write here. Okay, so we are not going to prove this, we just state this. Let script A be an algebra of subsets of X, and the collection AI, which is a sequence of sets in script A, then there is a sequence BI of sets in script A such that Bn intersection Bm is empty for n not equals m, and we shall have union I runs from 1 to infinity Bi equals union I runs from 1 to infinity Ai. Okay, here in this result, what they are trying to convey, you have an algebra. Okay, what do we mean by an algebra? It is the collection of subsets of any set, right? So in that algebra, we initially have some sequence of sets. Okay, which means we are basically taking a sequence. In the sequence, all the members are sets. You have these things. In that situation, you are able to identify some other sequence such that all the entries of those sequence are mutually disjoint, right? Then when you make the union of the new collection of sequence that you have taken, that is same as that of making the union of the sets, the sequence of sets that you had. Okay, so it is more or like, let me try to give you a picture kind of representation. This is not the exact thing, but to make you understand, I can give you this. Okay, let just a minute. Okay, so let me name them as a1, a2, a3. Let this be a4 and let this be a5. So likewise, you have some countable collection. Okay, sequence means entries of the sequence are a countable set, right? that is the distinct entries of a range of a sequence, is a countable set. So initially I just gave you this idea. Now with this, what we are going to do is that you can fix whatever you want initially. Okay, so let me fix a1. Let me choose my a1 to be b1. Okay, so what I have done, I have chosen this part completely. Now I'll have to identify my b2. So from my b2 is going to be a2 minus a1. So from a, so this is going to be my b2, right? Next, let me find my b3. So my b3 is going to be only this part. b3 is what? Which is a3 minus a1 union a2. If there are some points in common, those has to be removed from a3 to get b3. Next, we are about to find out b4. So b4 is only this part. That is what? a4 minus union I runs from 1 to 3 ai, right? Next, what is remaining? We'll have to identify what b5 is. So this part is going to be my b5. So b5 is what? a5 minus union I runs from 1 to 4 ai. Okay. Now, when you make the union of all these things, you can very well see that is union I runs from 1 to 5 ai is same as that of union I runs from 1 to 5 bi. Okay. Whether you are given with some disjoint sets or not, that is not a bother to you people. You can always disjointify them. That is the ideology that is given in this result. We will make use of this results in the upcoming lectures, like in the upcoming theorems and lemma's propositions that we are going to do, right? Okay, moving further, now let me produce you some examples of sigma algebra. Okay, so from these two definitions you may very well see that all the sigma algebras are algebras, whereas the converse need not be true. The first example is, you consider any set, okay, and here I'll have to do a, right? So that is, let me write it as 2 par x, which is what? R set of x. That is all possibilities of subsets of x. Here you may very well see that here we have considered all possible subsets, right? Therefore, of course, the union is going to be inside it, intersection is going to be inside it, the complement is going to be inside it. It is trivially a sigma algebra, right? Next example, in this example also, your access any set. Here, your A is going to be simply the empty set and the entire set. Okay, why is it so? Here you may very well check. Here one you have only two possibilities. If you collect phi, it is phi. If you consider x, it is x. Phi union x is x itself. So only these three are the possibilities. Next, phi complement is x and x complement is phi. This is done. What is the third condition? Third condition is either you have phi with phi, or x with x, or phi with x. Only these three are the possibilities, right? See, here you will have phi, here you will have x, here you will have phi. All the three conditions are satisfied, therefore it is also a sigma algebra. The third example that we will see is, here also you consider x to be any set. Now you will have to consider a subset of x, be it any subset. You will have to consider a subset of x and which is not equal to x. So therefore the strict is considered here. Next, consider your script A to be phi x a complement. Okay, here if you try to look for the verification of the script A to be a sigma algebra, you may very well see it. Okay, let me just give you the hint. Any set with itself, be it union or intersection, it is going to give you the same thing, right? And phi with any set will give you the same set. X with any set will give you x. Okay, the question comes only when you make union of phi with a, sorry, when you make the union of a with a complement. We have seen all other possibilities, right? So it is going to give you x. Okay, the complement of a is a complement and the complement of a complement is a itself. Okay, complement of x is phi and complement of phi is x. So that is also verified, right? And what is the third one? You will have to make the finite intersection, right? So here let me give you the ideology for only two different sets, and finally you can club them up, right? So when you make the intersection of phi with any set, it is going to be an empty set. When you make the when you make intersection with x, you are going to get the same set itself. If you make intersection of a and x, you would get a. If you make intersection of a complement with x, you would get a complement, and the intersection of a and a complement would give you phi, right? That is also, that can be verified. Okay, I have given you the ideologies that you can verify. Here script A is the smallest sigma algebra containing the set A. Okay, now at this moment I would give you an exercise, a basic exercise, that is, let me take my, okay, be it xb, let x be any set. Okay, so a1 union a2 union etc till union aj, where aj are disjoint. You will have to identify the smallest sigma algebra containing aj, where j runs from 1 to n. So you will have to identify what is the smallest sigma algebra. Here I have given you a set. I have not spoken about the type of set, that A may be written as union of several sets, right? So okay, be it J itself. You try this out. Okay. So with those ideology, we will now move to the concept of a measure. But before moving to the concept of measure, I would like to give you something called Borel sigma algebra or Borel sets. I don't know where to write. So I think I can manage with this space. Okay, this is the next example, right? You can have that way. So here consider Rn. Okay, now we are going to define Borel sigma algebra of Rn, which shall be denoted as script B of Rn, okay, which is the smallest sigma algebra containing all the open sets of Rn. So in simpler terms, script B of Rn is going to be the intersection of script A, where your script A is the sigma algebra of Rn. So when we say sigma algebra of subsets of Rn, and this contains all open sets. So can you identify some non-open sets in Rn? Yes, of course, you will have to think of them as well. So you will have to be very clear with what do we mean by open sets and closed sets in Rn. Only then you can see what is this, right? So before moving to the concept of measure, let me tell you something. Okay, so this is in continuation to the previous thing that we were discussing. So more generally, if you have some A which is okay, here let me use different notation. Here there we have A, okay, be it anything. If you have some A or F, script F, if it is a collection of, if F is a collection of subsets of X, then sigma of F is the sigma algebra generated by A. So this has nothing to do with the Borel sigma algebra. Here, if you notice the exercise that I have given you people, you can understand what I am trying to say here. Okay, just try that out. I think I shall end this lecture by this. In the upcoming lecture, as you can see, we are going to talk about the concept of measure. Actually, this is where we are entering into our course measure theory. We have just seen some basic ideologies that are needed to study measure theory. Thank you. We'll meet in the next lecture.